Welcome. We are going to look at a binomial experiment right now and the steps to design and conduct one. So we're going to look at the probability of two coins both landing on head, or I should put heads. Each of them heads, not tails. So step one, we have to define the trial. So in this case, the word trial means the actual things you're going to do, or the set of a thing that you're going to do a certain number of. And here's what it is. I'll put this in blue. A trial is, get this where we can see it better, tossing two coins 20 times. Now we're going to look at what step 2 is. For step 2, we're going to define what a success is going to be. Define a success. So a success is both coins landing on heads. Okay, that's step 2. Oops, put that one in black. And I'm going to put a box around step 1 and a box around step 2 so we can see these as separate things. Now let's talk about the theoretical probability of success, and that's going to be underneath this. The probability of actually getting this, of landing on heads, that's what we're going to look at here. Okay. Theoretical probability of success. I think we can call this step 3 because we know from step 2 now what we want to get. Step 1 is what we're going to do. Step 2 is what we want to get. And now for step 3, let's determine the possibility of actually getting that. Theoretical means what should happen, not what actually does. Steps after this we'll go and do what actually is. So for the theoretical probability of success, let's sort of do a way of thinking about a drawing that shows this. So we have two coins. When we flip one, we can get heads or we can get tails. So I am going to actually list the possibilities here by doing it this way. Possibilities. One coin gets heads and the other coin gets heads. The first coin can get heads and the second one could get tails. The first coin could get tails and the second coin could get heads. The first coin could get tails and the second coin could get tails. There are no other possibilities. These are the only things that can happen. And that means that there are 4 possibilities. So over here I'll put success, or successes, is heads, heads, and of that there's only 1. So what we get is the successes are 1, the totals, or total, is 4, so we have a 1 over 4. What we do is we do a fraction of success over total. And that's a 1 over 4. which can also be written as 0.25 or as 25%. So that's the probability of success is 1/4 or 0.25 or 25%. Now conversely, I'm going to put this as red underneath it, is for failures. Failures are the opposite. If there's one success, that means there's 3 failures out of 4 possibilities, which can be seen as 0.75 or 75%. Okay. So now we see what should normally happen. If we flip these coins 1,000,000 times, 25% of the time they should come up heads, heads. 75% of the time it's going to be something else. Now, let's actually do it. Not 1,000,000 times, but we'll do it a bunch of times. So here what we're going to do is define a random variable. Define the random, that should be a D, and let's make sure it's more obvious, random variable. So I'm going to use X. X represents the number of successes in 20 trials. So remember, a trial is tossing 2 coins, and in 20 of them, and that's what we're going to do. So we're going to use on the calculator the random number generator. Random number generator. So it will give us actually results as if we were tossing coins. And the way we get to it, you go to, on the calculator, you go to the math button. I should write math first. And then you move over to the probability button. Oops, not the thing I wanted to hit, this one. And then you move down in the probability button to R, A, N, D, and INT. Oops, nope, not parentheses yet. INT and then parentheses. So that's what you're going to see here. And so you're going down that one. And you're going to get to that, and what I want you to put in, you're going to see this on your calculator when you pressed rand INT parentheses. That's random integer. So number, in this case, they'll do an integer. And you're going to want the integer to be between 1 and 4. So you're going to put it this way. And what that means is 1, 2, 3, 4. And so I'm going to come back up here. 1 will be heads, heads. 2 will be heads, tails. 3 would be tail, heads. 4 will be tails, tails. And of course, we want the successes, which is 1s. So, step 4, no, now step 5. Step 4 was define that. Use random number generator 20 times. So when you do that, you start counting them up. And so you want how many times you get a 1 and how many times you get 2 or 3 or 4. It doesn't matter how many it's one or the other, it's just that it's not 1. And so I do this and I do it a bunch of times, and I did do it earlier, and when I did, I got 2 of these, and I got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2, 3, 4, 5, and then another 1, 2, 3. So what I got were, of the ones for successes, I got 2. 2, 3, 4, which were fails or failures, I got 18. So what does this look like? Okay, that means that, let's come and write it down here. So success, I had 2 over 20, which is 1 over 10. But theoretically, I should have had 1 out of 4. So 1 out of 10 is 10% or 0.10, and 1 out of 4 is 0.25. That's a pretty significant difference. So results. Results of this experiment. The experimental probability of 0.1, or I'll call it 10%, is significantly lower than the theoretical probability of 0.25 or 25%. If that had been 20%, I'd say it was pretty close. 15% I think is pretty far, but 10% is way below the 25%. And that's what we put. If it was a little above, like 30%, we might say still reasonable. And that's where we go with finding theoretical and then experimental probability. So let's review this on here. Step 1, you define what it is you're going to do. You define what a success is, what you want to have happen. You figure out the theoretical probability of getting that success. Then you do an actual experiment, steps 4 and 5. 4 sets up the experiment by figuring out what the x is, what do you want, and you then write it, you do it on a calculator in this case. You could do it by hand. You could take 2 coins and just do it 20 times yourself, or do it, say, 50 times and see if you get closer to 25%. Chances are you'd good, but hey, do it. Go ahead and try it. Then you actually do it and then look at the results. I think actually we should call this step 6. So results. Okay, so that's where we have now finding the theoretical and the experimental probability. Let's use that. Let's look at the next page and let's use a somewhat, practical or real life business problem here, or just sort of let's play around with this idea. A candy company produces strawberry and vanilla flavored candies, 65% of which are strawberry on average. The production line mixes the candies randomly and packets 15 per bag. What's the probability that 7 candies in a bag are strawberry? Well, if you don't like strawberry, you'd really like one of the bags where very few of them come in. But there's a general, if you do this a million times, then most of the time you're going to get it very close to 7 candies in the bag this percentage of times. That's what we're looking for. What's that percentage? So we're going to find this out. So I'm going to put a line here. And so we're going to first figure out what's a success here. So a success here is 65%. We want the probability that 7 candies in the bag of strawberry, 65% of these candies are strawberry. So actually, to some extent, that's just it. It's 65% is the success. Failure would be the opposite. Failure is 100 minus the 65, or 1 minus the 0.65. So it's 35. And that, of course, is 0.65 and 0.35. And here's what we do. We set up a binomial with success and failure. So I'm going to write it this way. Success plus failure. And the total number of candies you get in it. Out of that 15, some will be successes and one will be failures, meaning some will be strawberry and some will not be strawberry. And that's where we think that if that's the success, that'll go here. And if that's the failure, that'll go here. So let's actually next write this down over here. 0.65 plus 0.35 to the 15th power. Now, notice that these two things equal 1. They always will add up to 1. And that's because your total of the successes and failures are the total of everything. You can't have some neutral ones. You're just always going to have successes or failures. I suppose in a different way you could have them even, but even then some of them will be success and some will be failure, so it'll be half and half. So it'll still add up to 1. But now we're going to use that binomial and we're going to expand it out for essentially what would be if there are 7 in a bag that are strawberry, that's like the 8th term in this. So we are going to figure out a few things and use a formula very similar but not exactly the same as the binomial expansion formula for a single term. So this is the formula we'll use. I'm going to put it in green here. NCR PR Q N minus R, and this is P and this is Q, P, Q. So a way you'll often see this, and I think the way the textbook does it, is P plus Q to the nth up here. Okay, so knowing that, we know that P and Q are these numbers here. N is the 15. So actually I'm going to write them over here. N equals 15. R is the 7. P is 0.65. And Q is 0.35. Very important, and it's much easier for you if you simply just list these, and then you can put them in the formula. So since I'm going to be able to use the calculator for this, I'm going to use NCR. I could do it in the other methods. Now using the Pascal's triangle would be harder with 15 so high, but it is, possible. And doing it with factorial is definitely still possible, but it'll be easier using it with the calculator. So I'm going to set this up as 15 CR, C7. So it's 15 things, 7 of them taken at a time. And because it's 7 strawberries that you want, strawberry candies. And the P is 0.65, and the R is 7, so we'll put that in there. And the Q is 0.35, and that's 15 minus 7, and I'm just going to change it to 8 here. And then you put that in the calculator. If you put that in the calculator, you put this in the calculator, remember to go to probability, and then go the third one down. But you have to put 15 in first. You have to put 15 and then do math, probability, and it's the third thing down. Then, when you press enter, you press 7. And you're going to get a number that you're going to multiply. In fact, I should pull that one out because I just wrote the answer on my own notes, but I don't think it'll hurt for me to do math, probability. Hold a second. Get my calculator to do it the way I want. Probability. So I'll put 15. Go to probability. NCR. Put the 7. And for this number, I would get 6,435. So 6,435 times whatever that is, times whatever this is, 0.35 to the 8th. When you put all of this into the calculator, you're now going to get 0.0710. So it's 0.07, but if we move the decimal over twice, we'll be able to keep that 1 in there as a tenths place and have 7.1%, and that would be our answer here. And that question, back up here, what's the probability that 7 candies in a bag of strawberry? So it's 7.1% probability of 7 strawberry candies out of 15. And that's exactly 7. It's not 7 or 8 or 9 or 10 or 5 or 6 or 7. It's just 7. Not more and not less. We can also do this kind of thing to figure out if it is going to be 7 or more, or up to including 7 or not including 7. So let's look at an example where that's a problem kind of thing. And first, let's just quickly review here that we looked at successes and failures to the power or the number there, and that was these numbers, 0.65 and 0.35, because those were our percentages for success and failure, and the 15. And using this formula and identifying N and R and P and Q, we are able to just multiply it out using the tools we have, like the calculator or by hand, and getting 7.1%. Let's look at this problem. Family has 4 children. Determine the probability associated with the number of daughters by calculating the distribution, assuming that there's a 50% chance, female or male. This could be done with sons as well. I have 1 son and 1 daughter, so it's like random that I chose like my daughter for this one. Anyway, let's work it out this way, because that's just sort of the shell of the problem. Let's figure out the math that's involved with figuring out the probability. This time we're not going to figure out the probability of just one thing, but rather the probability when there are 0 daughters, or 1, or 2, or 3, or 4, and the kind of question we're then going to answer is at least 3 daughters, although we could do many different variations of that. This kind of thing, once you've done the first part, A, you can then answer numerous questions based on the results. So we're going to look at the same basic kind of setup here as P plus Q to the 4th power, or actually I should say to the nth power, so that P is success, or your successes, Q is your failures, and N is the total, or total number, I guess, which is given by the total that you have there, the 4. So we also are given the 50-50% chance. So what we actually have here, 50% is a 0.5, so this becomes 0.5 for success for the number of daughters you would have. But if you have sons, it would be 0.5 when you want daughters, or the other way around. You know, if we wanted sons, it would be 0.5, and daughters would be 0.5, so it would be the same. Okay. And here we have 0.5 plus 0.5. So not really a want, it's just what happens. So the chance of getting sons and the chance of getting daughters is half and half. So, oh, and I meant to put a 4 here because now I'm putting the numbers instead of just the letters. So what we do is we expand the binomial. Expand 0.5 plus 0.5 to the 4th power. And that means we're going to need 5 terms. And one of the things to get the coefficients of the terms, now we can easily use Pascal's triangle because the number is small enough. 1, 4, oops, 6. I'm jumping too far ahead there. And this row, because the 4 is here, tells us that's for the exponent 4. And those will be the coefficients of our terms. So let's expand it by putting the first term here, and then I'm going to put the second term here, and the third term here, fourth term here, and the fifth term here. And I know already that my first coefficient will be 1, and here it'll be a 4, and here it'll be a 6, and here it'll be a 4, and here it'll be a 1. And then I have to put the P and the Q. So it's 0.5 and the 4. We take that exponent, and I don't have to write it, but I will just because as a teacher I feel like I have to put each little thing down. And this means that these two exponents add up to that 4. And now we start going down. 0.5, 3, 0.5 to the first, 0.5 squared, 0.5 squared, 0.5 to the first, 0.5 to the third, 0.5, 0, and 0.5 to the fourth. So in each of these cases, these add up to 4. So every time they add up to 4. Well, now we actually have to multiply them. So if you multiply 0.5 times 1, you get 0.0625. And I'm going to move the decimal over and make it the decimal of 0.25%, or 6, not 0, 6. Move it over, 6.25 or 6.3%. The second one multiplies out to become 0.25. So that's a straight shot of 25%. The third one is 0.375, which means it's 37.5%. This next one, it's a mirror image of the second one, so it's also 25%. And the first one is a mirror image of the last one's a mirror image of the first one, so that one's 0.0625 or 6.25% or 6.3% if you wanted just to keep to one decimal place. Okay. What's this mean? Well, this is the chance because this one is for the number of daughters. Number of daughters, number of daughters, number of daughters, number of daughters. And this exponent tells us it's 4 of them, 3 of them, 2 of them, 1 of them, none of them. So that means that that's the percentage chance of getting 4 girls. 25% is the chance of getting 3 girls. Or boys if you want to switch it around to the boys. Okay, this is the chance of getting 2 girls. The chance of getting just 1 girl is also 25%. And the chance of getting no girls is 6.25%. Okay. And from that, we can now answer a number of questions, including the question that was done here in B. So first, A is done. This is letter A completed. Oh, I should do a better A than that. Okay, that's a little bit better for A. So we now have a probability distribution of all 5 possibilities. And for B, the question is, what's the probability of at least 3 daughters? Well, that means we could have 3 daughters, but we also could have 4 daughters. Because if there's 4 girls, then that means there's at least 3. There's 3. There happens to be an extra one. What do you do with an extra one? Well, in my opinion, you just be happy you got another one. So here, but that means it's these 2 together. So you would add the 6.25% plus the 25%. So what you would get to here is a total of, 31.25%. So 31.25% would be the answer for B. I could ask it differently. I could say at most 2 girls, meaning that at most would mean 3 would be too many and 4 would be too many. And then I would be looking here at these 3 to add them up, which would be the opposite of the 31.25. So it would be, 68.75? Or I could say at most 1 girl, in which case it would be just the 2 here. So there's numerous questions I could now ask, and that's where these words of like at least or at most or more than or less than, you want to think very carefully about the words and therefore what it means. Now I'm going to put in one other thing here to mention about this, and this is called expected value. And it's something you'll encounter, so it will be good for you to hear about it. So expected value is to find the average or the mean of it and then use that. So we are going to use, usually the average we show like that, but we're going to show it here as this like U symbol. Okay, so I'm just going to do that. And so what I want to find is the mean. And this is sometimes used in statistics too, this little symbol. So I'm going to put it here this time, get you used to it. So I think that's an, not epsilon, it's a, I forget, it's one of the Greek letters. And they use it for this. And they're going to say that this is equal to NP. So N is the number of trials, which in our case here was 4, okay, because that was that exponent. That's what we would use for it, the main exponent. And then here, the P is the probability of success. And we know that the probability of success was 0.5. So what we do is simply multiply that. 4 times 0.5. And in this case, we get a nice, simple, easy 2. So that means the way we would write this is the expected, like the theoretical probability. The expected value, in this case, the value is the number of girls. So the expected number of girls in a family of 4 children is 2. And we figure that out using this little formula of the number of trials times the success. So that's sort of an extra thing that's not specifically the distribution, but you use the information in figuring out the distribution to get this expected value. All right, so you have seen now, to go back to this in the beginning, the designing and conducting of a binomial experiment. First finding theoretical probability of success, and then finding, using the random number generator to get the experimental probability of success by experimenting. And then we find a probability using a specific formula, right? That this formula here, and I think I'll make it easier to see with n, doing it in black here, and PR and QN minus R. It's not exactly the same as the one for finding a particular term. So make sure you're aware of those differences, of the difference in the formulas. And then we did a full probability distribution with all 5 possibilities, and then the kinds of questions we could ask based on that, and then finding the expected value. I hope this was helpful in understanding these and that it made sense to you, and thank you for watching and listening.